How are you guys doing last night? So I actually spent a lot of time remaking the slides for today. So if you have the habit that you want to use the preview slide, you probably want to download the new one from the row I have on the schedule today, because people tend to have a feeling like, okay, if that used to work, then let's don't touch it, right? And sometimes it's not perfect, but I just keep reusing it. And some slides that originally scheduled for today was like that. And by yesterday, I finally feel like, okay, because a lot of good discussions that I got from you guys, so I really should do something differently. So let's try to see if it works well. And if that will probably be the next decades of slides that I will be using. But before we start, it's always important for us to remind us where we are coming from. So let's say MDOS will tell us that we should find the most critical problem. And now I think nationwide, worldwide, we all agree that there is a huge gap between performance of memory and store and your processor. So to bridging the gap, we put a lot of intermediate stuff that's the levels of different levels of SRAM caches in there. So typically, the L1 cache, they are smaller, but because it's small, so we can make it faster. L2 is larger than L1, and because it's larger, and based on the circuitry characteristics, so it can only be slower because it's larger. So turns out, and the way how we manage it is totally a hierarchical structure. So most of the time, you can very safely assume that in most of the processor architecture, the lower level memory, the upper level memory hierarchy, when I say the upper, is the ones that are closer to the processor core. So those are smaller, but they are also considered as the subset of its next layer. So L1 is a subset of L2, L2 is a subset of L3, and L3 is a subset of your DRAM. And as you read the book, you already know that the DRAM, even the DRAM is a subset of your virtual memory. So everything is a subset of others. However, as we mentioned, when we are closer to the processor hierarchy, we want the stuff to be captured. The hit rate should be higher, but we also want it efficient. So one of the solutions that we make to ensure we are not having too many conflicts, but also not too slow when we access it, is that we make it set associativity. So by making set associativity, it means that every address is hashed to a certain set, to a certain set. And when we are going to look up for that block, or when a block is amiss, we want to find it, put it from located from the lower memory hierarchy. It can only be there. So if you want to look for that block, or whenever the block should show up, it should only be in a set. And each set would have multiple blocks so that we can avoid the collision problem. So that's the set associativity cache. And when we try to access the associativity cache, we have to partition the address into tag, index, and offset. We use the offset to address which byte should we start the output in your mux. And we use the index to figure out which set may contain the block that you are looking for. But to know if this is indeed the block or not, we have to compare the tag with the requesting address. So that's how we find out if it's a hit or not. And that's where we were in the last lecture, that we talk about, okay, so we want to know this in CSE142, even though we advertise this is not a hardware-oriented class, but you really need to know how the hardware works, so that the most important thing is that we know how does our software perform on this hardware. So it turns out you have to know this geometry of your cache to simulate the behavior of your code. And after we simulate the behavior of a code, we realize that there are 3 different types of miss. Compulsory miss means the first time we access a block in a program. And the second type of miss is called conflict misses. It doesn't mean that we are out of cache capacity. It means that because there is only a limited amount of blocks that each set can accommodate, so we have the miss. And capacity miss is that, okay, let's ignore the set associativity thing. Even though I let your block go anywhere, it's still going to be a miss. So that's called capacity miss. So the last lecture, we ended at this NVIDIA Tegra X1 case. And there are some good discussion that coming up later and in the office hour as well as the Piazza Forum. But there is one mistake that I made, but nobody ever pointed out. So today I'm going to go through this example a little bit before we start the rest of the part. So first of all, for this part, okay, so first of all, this slide, that's okay. This slide has no errors there, right? So we know that without doing anything, on directly running this on an NVIDIA Tegra X1 is going to be 100% miss rate. And there are 2 types of miss that we are going to see here. One is called conflict miss. And again, as I said, the definition of conflict miss is that the block was there before, and the cache potentially still have capacity. However, they are not in a block, in a set that your block should be located. So you got kicked out, right? And then the next time when you want to revisit this block, there is a miss. This is conflict miss, right? So if you look at this sequence, right, when I try to fetch the block E0 contains E0, which is E0 to E7. When I try to fetch this in, I have to kick this one out. And when I get this in, right, because it was here together with A0 and A2 to A7. So that's a clear case, it's a conflict miss. However, when we keep going on, it's going to be conflict miss until we meet another boundary of the block, which is A8, right? So AA, that's another, that's the boundary, the starting of another block. And then we start to have compulsory misses again. And this is compulsory misses here because when we access A8, those are the first time we touch this block in this program. And then gradually you are going to see the same pattern coming up again and again. And that's how we get 100% miss rate. So in the last lecture, I talked about there is a way we can improve the miss rate of this code. It's basically a technique called loop fission. So the idea of loop fission is that if you think about the original code, the reason why we have all conflict misses is because we have to accommodate 5 blocks in each iterations, right? So if you look at these pieces of a code, right, you can actually do this 3 and this together and then separate the division. So this is, so now my feeling is that, okay, let's split this loop into 2, right? So this is called loop fission. And for loop fission, right now, the first loop, I only traverse E, A, B, C, right? So I only need to accommodate 4 different arrays. And even though they all map to the same set, as you can see, the only miss that I would pay when I entering the boundary is when I entering the new boundary of a block, right? So I'm only having compulsory misses here. And that's where we that's what this modification will help. We remove all the conflict misses now. And some of you yesterday were asking about, okay, so if you remember the code, right? In a second iteration, in a second loop, we revisit E again. But why are they not missed, right? So here's the thing. First of all, notice when we enter the new boundary of a block, they are in a different set. And because it's a different set, it won't actively kick out stuff from other sets. So those stuff are still remaining in index 0, set 0. They are all good. And this won't kick them out. And the other thing is that the only case we would have to kick out is that if somebody in this iteration would use index 0, right? But if you look at a trend, right, every time we are incrementing the set index by just 1. And how many sets do we have to visit? We only need to visit 64 sets. And for this cache, we have 128 sets. So you are only using half of the sets, right? So there's, first of all, if you look at this, first of all, there's no block getting kicked out after I finish this run. And the second thing is, we don't even use the full capacity of the cache because the cache has 128 sets, but we only use half of them, right? So there's no capacity miss and there's no replacement occurring here. So now, when we go to the next loop, okay, this is where I got wrong. So yesterday, I mentioned there are 2 memory accesses here, but in fact, it's 3. Because the code here was like divided equal, right? So if you want to divide it equal, first of all, you have to load E0 and then divide it by EI. So this is a read, this is a read, and then write it to EI. Right? So actually there are 3 memory accesses, but yesterday during the lecture I said it's 2, so that's wrong, right? So that's the correction I want to make. So there are 3 for here. However, within this 3, previously I should have convinced you that E0 is always being in a cache, right? So there is no miss here. And there is a compulsory miss because then when we access D when with an index that multiply 8, or say mod A, modulo A is 0, then it's a compulsory miss, right? Because that's a new boundary of a block, right? So in this way, you can see for this pieces of a code, so if you do a stats, right? So for the first iteration, first loop, you have a total of 4 times 512 memory accesses. And among this, right, you only get misses when you enter the new boundary of a block. And here, because we have 8 elements within a block, so there are 4 times 512 divided by 8. And for the second part of the loop, we have 3 memory accesses per iteration, and we have 512 iterations, so we have 3 times 512 as the total number of memory accesses. And then we only have 1 compulsory miss for every 8. So that's the total number of accesses, total number of misses, and the miss rate is still close to 10% as we mentioned. So is this all good? Are we all good on this question? Question?
So for the miss rate, normally I told that for the second one, will it be 512 over 8 divided by 3 times 512 for the miss rate?
Yeah, but when you look at the miss rate, you are looking at the whole program or say the complete part, right? If I'm asking you the miss rate, then for this loop, then you should just use this part. However, today I'm asking you this modification, how does this compare to the baseline? And the baseline was actually a combination of both, right? So if you said, well, the miss rate is just this or this, then you are misleading others. Sounds good? All right. Okay, so this mechanism is called loop fission. Basically, we are splitting a loop into 2 so that we can lower the miss rate when we traverse this data structure. So as you can imagine, this is the case where we are alleviating conflict misses. But now, I want to ask you about this, right? So if we have a processor from Intel, should we do loop fission or not? All right, let's take a look. Okay, so we have diverse answers. So why don't we discuss with your friends and let's see what do you guys think after discussion? All right. So after discussion, more of you think the answer is D. So before I show you the demo, I would like to hear what you guys think. Anyone would like to share?
Cache, less cache miss can result in better runtime because it requires less memory access.
Okay, so you think this version would give you a better cache miss rate?
No, I think it's with a fewer memory access will give better performance.
Okay, so can you talk about, okay, so here we have two things, right? Cache misses and memory references, right? So when we have an Intel Core i7 processor, do you think there's any difference or in terms of cache misses?
Not really. They only have the first time accessing issue.
Okay, so here's the thing, right? Previously we mentioned the reason why you want loop fission is because we want to avoid conflict misses. But is conflict miss an issue when we put this code on Intel processors? Not at all, right? But there's no free lunch, right? What's the side effect of using loop fission? Because you separate them into two loops, right? As I said, originally you only have 5 memory accesses per iteration. But because you separate it, right, if you check the code carefully, you got 4 per iteration in the first loop and 3 in the second. So you are actually having 2 more. And each memory access, there are instructions and they take time. So it's going to be worse, right? So if you don't trust me, right, you should at least trust the numbers that we run. So what if we run this as a from our demo machine? So this is okay. So this is okay. So this is on Intel. Okay, so let's do this. Okay, so let's try to run this on an Intel processor. So right now I'm rerun everything on this Intel processor. And this is what the demo shows, right? So with the demo, what you can see, with loop fission, I have 4.2 million instructions. And here I have 2.9 millions of instructions. So that's a huge difference, right? And in terms of cycles per instruction, that's not too different. If you think 0.9 and 1 is basically the same, right? But that tells you more instructions are basically going to give you more performance hit in this case, right? So if you check the execution time, the loop fission one takes probably 1.2 times, 1.16 times more than loop fusion, right? So so in this case, right, you should probably know that, okay, if conflict miss is not a problem, I shouldn't even use loop fission. And another lesson that you should learn is that why compiler doesn't actively split the loop. Because the compiler cannot make assumption. Where am I going to run this code, right? Even processors use x86 architectures. They have different number of way associativity. Like 10 years ago, AMD processors, they only have 2 to 4 ways because their foundry sucks. And Intel already have 8 ways at that time. So for that period of time, if you want to write a code that performs really well on AMD processors, you have to use loop fission. But if you do that, it will run really bad on Intel processors, right? And at that time, right, like Intel's market share is more than 80%. So people would rather modify their code for Intel than AMD, right? So that's why it's a vicious cycle for AMD at that time, because everybody is knowing that softwares are not optimized for AMD. So if you have an AMD processor, it's just going to be bad anyway, right? So even though how good their hardware is, right? So that was the issue at that time, right? But again, that also tells you why it's so important for programmers to figure out what kind of hardware, what kind of bits that we are dealing with, so that you know, should I use loop fusion or loop fission, right? But from what you learned so far, right, when cache has very limited way associativity, that's the time you would have a lot of conflict misses, so you should use loop fission to avoid that. However, if conflict misses is not even an issue, you should try to use loop fusion so you can reduce the amount of control overhead, potentially the amount of memory accesses, right? Okay, so now we are going to talk about probably the most interesting and difficult to understand topic. For the software optimization for cache-friendly code. And that's actually the part that I spent a lot of time remaking a slide yesterday. So before we start, let's recap on how we allocate a 2D array, because we are going to talk about metrics for now, right? So because the memory space in computer is basically linear, so there is not really a thing called 2D memory structure. So if you want to have something 2D, you have to basically reduce the dimension to 1D. But you still say that, okay, in my Python, in my PyTorch, in my TensorFlow, I do have the matrix data structure. How does that work? And even for C or C++, they have that, right? So basically, except for the last dimension, which is the lowest dimension, everything else is a pointer. So for example, if I have a 2D dimension, this is pretty much the initialization code. So first of all, I initialize a double pointer. So it's so showing that this is a 2-dimensional data structure. But then when I try to initialize the first dimension, you are actually doing another malloc, which gives you consecutive array, consecutive elements in an array as the next dimension. So most of the time, the memory allocator will give you consecutive address. So you can consider, although your abstraction, for example, like a 4x8 matrix, right? But essentially it's 8, 8, 8, 8, right? 4 consecutive rows in a memory. So that's so you can consider, if I have an aij, it's essentially a of I times n plus j, right? So that's the abstraction that we are living. So now, today we are going to talk about probably one of the most important problems. So we said matrix vector is the most frequently used one for inferencing. However, in data centers, most of the time, we spend a lot of time in training. And matrix multiplication is indeed the most important computation that we need for model training. So for model training, you need to use matrix multiplication. And the most naive way of matrix multiplication is pretty much like this 3-level nested for loop, right? So how to do it is basically that start with an a C ij, right? And the Cij is equal to a row of A. Ith row of A times j's row, j's column of B, right? So that's basically what a matrix multiplication is. And the algorithm class already tell you this is a older n-cubic algorithm. Although I know the I2A book, I don't know if you use that book, but they tell you there is something you can reduce it to 2.7, but because that constant is too big, so nobody actually implements that in real. So most of the time, the national-wide recognized complexity for a matrix problem is still order n-cubic. Okay, so now if I said a 1K matrix would take 2 seconds, right? What do you imagine how we would need for like 2K by 2K by 2K matrix multiplication? 16, right? How do you get 16? Because order n-cubic, right? And n is growing by 2 times, right? Okay, so let's have the demo and let's see if it's really if it's really 16. So here's the code we have. So this is exactly the matrix multiplication. And now I'm going to run it and let's see how much time it would take. Oops. It takes a while, right? Okay, here we go. So let's see. For 512, it takes really quick, right? It's about 0.2 seconds. And for 1K by 1K by 1K, as I said, it's about 2 seconds. You said what?
I said
16. How much is that now? It's 24, right? Okay, congratulations. Algorithm class is proved to be useless again in terms of performance estimation, right? So now we know the reason is probably because memory, right? But what kind of methods is holding us from getting the scalability perfect as what algorithm classes told you? All right, so, okay, I love this chart because that means that you need to discuss, right? So why don't we make some noise and discuss with your friends? Go. All right, let's take a look. Okay, so after discussion, okay, most of you think it's either D or E, right? So what's D? So D is capacity and conflict misses, and E is compulsory and conflict misses. So at least we all agree there is a component of conflict misses, right? So can some of you tell me where are conflict misses coming from? Why do you think we have conflict misses? Where do you think we have conflict misses? Do you want to say something?
I'm just going to do pure guessing.
Okay, sure.
Just because too many objects are stored in the caches and it reaches the capacity, so it starts wiping out, replacing the oldest data. So there are some data we are supposed to.
So you are saying about out of capacity. Then why is it not a capacity miss?
I'm not sure.
Okay.
I'm
Other thoughts?
There could be a conflict miss because later according to matrix multiplication, there could be a time where one of the blocks would have been kicked out, but then that same block might have been required again, but it's not there at that time. So
Okay. Where in the code do you see that's likely to happen?
You reuse a lot of the columns and rows when you multiply.
I reuse a lot of column and rows. But when I traverse the rows, they are pretty much in order, right? So who are going to incur the columns, right? So, okay, so here's the thing, right? Okay, so now let's say if I want to do matrix multiplication on the red element, which is 0, 0, right? What I need to do is that I want to take one row and one column, right? And then if I want to do like 0, 1, then I take the same row, but a different column, right? And when I want to do the green one, which is 0, 2, I take the same row, but different column again, right? So here, do we have issue with A? No, right? So when you say row, that's why I'm stopping you from there, because row is by far not a problem yet, right? But how about the columns? Are we okay with that?
For now.
For now, you think it's okay? No, it's not okay for now.
not necessarily.
Okay, what do you think?
Because the thing is, as stated, the columns could be reused. So I don't know the exact depth that whether when it will be reused or like what exact time, but there's a very good likelihood that no, actually these will be reused, but I don't know whether it will be reused because of a miss or is it already there?
Okay, you know, so for to know this, you really need to write down the address sequence that we have, which I already do it for you, right? So first of all, for the column, right, I'm changing the first level index in the array. So I'm doing B0, B0, 0, B10, B20, B30, B40, etc., right? And if you look at, if I write down their address, so I randomly pick one, which is 20,000. And most of the time you can safely assume that because like they are going to be consecutive anyway, so it doesn't matter where you start. So now I start with 20 because it's easier for us to show it on the slide. And if you partition the address into tag, index, and offset, you will learn that, okay, surprisingly, right? First of all, because the row dimension is 2K. So as I said, right, your address, your array index is basically I times n plus j, right? So based on that, right, you can consider each column element. They were different from each other by the address of 0x4000, right, which is equivalent to 16K. So if you put that, it's not too difficult for you to generate the address sequence like 20,000, 24,000, 28,000, 20C,000. By the way, I like to use hexadecimal to count my age. So most of the time I can tell people I'm still in my 20s, right? Something like that. Anyway, set that aside. But the thing is that if you look at that, the index of every column element, they are always 0. But they all have different tags. What does that mean? Different blocks to the same set. What does that mean? We are going to have a lot of conflict misses, right? Because whenever I pass the boundary of 11s, when I enter B12, I have to start kicking out stuff. So when I revisit the next row, when I increment J, right, when I want to revisit B01, it will be a miss. So what does that mean is that B is a forever miss if you don't do anything. B is a forever miss as long as you have more than 12 elements in 12 rows in your matrix. You are going to see this. B is always a miss, right? So like, okay, do you a favor, right? If I go to B1, right, you can see everything is a conflict miss now, right? So this is definitely conflict misses in B, right? Okay, let's set B aside. If we just look at, some people may say, well, it's just because you don't have sufficient amount of associativity, right? But you said the capacity is an issue, right? It's indeed an issue. If you think about, we have, okay, even though we can completely ignore the conflict misses in the columns, right? And we have some way to deal with, for example, like we have a column store or something. It's still going to be an issue. Because if you think about the capacity of your cache, right? It's only 48 kilobytes. And each row or column is 2K elements. So to completely store a row or a column, you would actually need what? You would actually need 16K for just a row or a column, right? And for this pieces of code, it's so easy for us to surpass the capacity, right? As long as I have the fourth column in, I have to kick out the first column already, right? So capacity miss as well. So not only conflict miss, but also capacity miss, right? So you can safely say, right, it's capacity miss and conflict misses. Any thoughts about this? Any questions so far? Okay, so now, do you have any thoughts? How are you going to address the conflict misses and capacity misses? Any thought? From what you have learned so far, how are you going to address the conflict miss?
Switch to GPUs, kind of stuff.
Come on, forget about that, right? If you only allowed to use And this is still an issue on the GPU. Because for GPU, right, you still have way associativity cache, and you have limited amount of LUs. So you still have no way to accommodate all of this. Any thoughts? What? Fission, right? So the basic idea of loop fission is that we break up the computation into different loops, right? But how do you see the potential here? It's similar concept of fission, but you have to do it differently.
So you calculate row first, and outside of this row.
But when I want to calculate the row, right, I also need the columns, right?
Yeah, or dissect the matrix into smaller pieces.
Okay, make it into smaller pieces. But how can I make them into smaller pieces but also guarantee they are correct? No idea, right? But okay, you guys kind of like get it, right? If I want to reduce the conflict misses, I have to restrict. Okay, so where are we having a lot of conflict misses? Because we visit too many rows for a column each time, right? So we have to stop before we reach the weight associativity of the cache, right? And for the rows, we cannot go for too long. Otherwise, it will occupy the whole cache, right? So we also have to restrict the size of a row that we visit every time, right? So if you are, so basically what means is that you have to partition your computation, or say fission your computation on the row and also the column, right? So if you partition both row and column, that's tiling, right? So that's why we call this matrix tiling. And mathematically, that's actually possible, right? If you look at how we calculate an element in matrix C, it's basically the sigma of, so Cij equal to the sigma from I to k with aik times bkj, if you are more comfortable with that, right? And you can split it, you can separate this into two sigmas, right? One go from 0 to half, and the other go from the second half, go to the second half. Or you can split each half into quarters, right? And gradually, you can partition it indefinitely, right? So that's the whole idea, right? So if you apply that, you can actually try to think, can we break up the multiplication and accumulations into something that would fit the cache really well? So let's go back to this, right? So here we said, because each way can only accommodate 8 blocks, 12 blocks, right? So if we want to choose a 2 to the something as a good number that we want to partition the computation of the column, what number will you pick? What? 3? Why is 3? Less than 12, but don't you feel like 3 is too small? We can actually go up to 8, right? 8 is still smaller than 12, right? So every time we compute 8 elements from a row and 8 elements from each column, right? So let's see how that would play, right? So now look at this, right? So right now, if I'm doing a first element, right, I only fetch 8 elements from each row and column, right? And remember, 8 elements horizontally is a block, right? And here, although for B, right, we are fetching 8 elements, but because they are not physically consecutive, and from the previous slide, you should be aware that they are 8 different blocks. Right here, we have 8 different compulsory misses, but these 8 blocks are now all in the cache, right? Agree with that? Okay, so when I get the, but here we are basically having 1 compulsory miss for the row A and 8 compulsory misses for the B. Now I'm doing this orange, which is 0, 1. And again, I restrict my computation to the first 8 elements of a row and a column. And I want to access the first column. However, when I create a compulsory miss for the zeros column, I already bring in 0 to 7, right? So this is going to be a hit. Agree? Right? And because we only have 8 blocks from B and 1 blocks from A and 1 block from C is 10, smaller than 12. So everything is in a cache. Agree? Right? So with that, if you continue to iterate, you will figure out that here at this moment, we only need 1 block in C, 1 block in A, and 8 different blocks in B. That's a total of 10. Everything fit in just one way in a set, one set, right? And even though I go down to the next row, right, I can still reuse the 8 blocks that I have for B without incurring anything except for the compulsory miss to get the second row. Agree? Right? And with this way, right, I'm just keep traversing down to the row and I don't reuse the previous row. Right? So basically, until the end of this 8 by 8 tile, I'm only seeing 8 compulsory misses plus in A and 8 compulsory misses in B. And in the meantime, I have 3 times 8 by 8 memory accesses. So now you see the memory L1 miss rate is only 8%. A lot better, right? It's a lot better, right? And okay, so if I want to continue reuse those 8 blocks in B, I can definitely keep going down, right? For example, like if I want to compute the purple, I can continue fetch the A, right? And until the end of the left half of the A matrix, right? And everything here, although we keep kicking out the rows of A, right? But it's okay because at least for a short period of time, I'm not going to revisit A0, right? And all the B's, the B tile are still in there, right? So at this moment, you are seeing a cache miss rate that is only close to 4.2%, right? So this is the thought we have, right? And now you guys might be wondering, okay, we still have the rest of the work that we have to do for C00, right? So how are we going to accomplish that? So the thing is that, okay, that we can continue doing the work by fetch the second half of the zeros row of A. However, this is already crossed the boundary, and because this is the neighboring block of the original first block of A, so it's actually a different index, right? So it's going to be a different index, so it won't kick out anything in set 0, right? However, what's interesting here is that when I am doing the second half, I also need the second half, right? So then I will start to kick out these columns, right? So you can imagine when I work on this bottom half, I'm actually kicking out the top half from my cache. However, this is also okay because right now I'm just working on this and this. I don't need this for a while, right? Question?
No.
Okay. That's how the concept of matrix tiling work, right? So if you want to implement this concept, because this is not a coding class, I'm just telling you the result, right? If you want to implement the concept, first of all, you need, again, because it's essentially matrix multiplication within each tile. So you still need a 3-level nested for loop in each tile to perform exactly like your matrix multiplication, but in just within this tile, right? Restrict your index within this tile. So that's why You see, start with an I, and then only stop at the at the I plus tile size, right? And because we want to perform all the necessary combination of tiles, so we need another 3-level nested for loop to make sure that all the necessary computation are covered. So the resulting tiled matrix multiplication would be a 6-level for loop, because we need the 3 to perform the matrix multiplication within the tile, and the other 3 to make sure that we traverse all the necessary tiles to accumulate the values correctly. So how effective is that? So let's run the demo. So this is the original matrix program, and this is the tile matrix multiplication. And this is the part that I skipped because, as I said, the last time I have a script to partition the address. So this is a different size. But as you can see, we still got a lot of column elements mapped to the same set, even though it's a different case. So now I'm showing you this tiled matrix multiplication code. So this is my code. See, exactly the same as the one that I show on the slide. And as I said, right, I picked 8. So right now I'm going to use 8 for all the cases that I have. Oh, shoot. Okay, do this. Now let's compile it and let's run it, see what values we got. So again, this is matrix problem, so it might take a little bit while, but hopefully this would be a lot faster. Is it faster? Hello, hello, why is it so slow? Shouldn't be this slow, right? Is it because I run too many or anything wrong? Hello, hello. This is too slow. Really? Is it this slow? I can't believe that. No, there must be something wrong. Is there? Oh, here we go. Okay, it's really that slow? Can't believe. Okay, so look at that. Oh, okay. So the top version is the baseline, right? What we got before. So before, remember, for 1K by 1K by 1K is 2, and 2K by 2K by 2K is 24 seconds. So those are our baseline. So right now, I am running the tiled version. So as you can see, the size is 512 with tile size 8. The execution time has been brought down from 23 to, 17 to just 7, right? 17, what was that? Okay, I would say 0.117 second to 0.007 a second, right? Twice. Now, for the case where we spend 2 seconds, is right now only 0.42, right? Very significant, 4 times faster. And for this one, actually not 4 times, it's 5 times. And for this one, originally 24. Now, only 4. And if you look at this 4 divided by this, it's roughly 8 times, right? So what does that mean? Computational complexity is not wrong if every operation is equivalently fast. And the thing is that cache miss is extremely slow compared against other operations. So if we can alleviate cache misses, we are actually making our algorithm following the trend of the algorithm complexity. So sometimes if you see your performance is not go with your complexity, it's not because the complexity is broken, it's because your code is broken. Okay. So, and even with 4K, right? I didn't run 4K. before. So that's why it takes so long, right? Even with 4K, right, it's roughly like around 8 times more than the original one, right? So some of you might be asking me, why am I pick A, right? Here I pick A just because I think it's a good number, right? Because we have 8 elements in a column, in a block, right? And we have 12 ways. So as I analyze, it should fit everything in. However, is that the best choice? So right now I'm showing you the comprehensive comparison regarding if A is a good choice or not. So if you look at this, right, here I run 2 other configurations. Three other, 4, 16, and 32. So look at 4, right? It's actually even slower than 8, right? So partitioning it further is not a good idea because you have more loop iterations. So one evidence is that if you see the instruction count, right, then it's actually inflated a lot, right, by 1.25 times more instructions because now you have more loop control that you have to go because originally you only need to jump to a different iteration every 8 times, but right now it's 4 times, right? And another one is interesting point is 16. So if you look at 16, it actually performs even better than A, right? Why, right? Because theoretically, through our analysis, 16 should not be a good choice, right? Remember, we have only 12 ways, and 16 is definitely going to surpass that. But why 16 is working here? So again, cache miss rate is not the only thing that would determine your performance, right? So I actually have a slide summarize this result. Let's see, where's my mouse? Okay, so this is my, here's a summary of the result, right? So first of all, the interesting thing is that if you look at 8 and 16, theoretically, A should be better than 16. And that's actually true if you look at the miss rate. 8 only have around like 1% miss rate. However, for 16, we have 7% miss rate. But the problem here is, if you look at the instruction count, right? And as I said, the instruction count actually matters, right? Because of the loop control that we added. And the loop is controlled by some kind of instruction called branch, which later half of the summer session you will learn. Branch is also another low latency operation. So if you have more branch, you are going to kill your performance as well, right? So there is no golden rule what's the best tile size. And in fact, if you run the same algorithm with smaller data size, 8 would be a better choice, right? So in your programming assignment too for the lab, you will practice this kind of trick a lot. And it doesn't, so sometimes the number, you really have to do a lot of experiments to find the best one. But here, I'm just showing you, right? Like simply look at the miss rate is not the only thing determining the performance, and there are also some other factors. So how to determine the best tile size in tile algorithm is more about like experiences and experiments rather than theoretical analysis. But I think this series of slides should give you a pretty good idea how tile algorithm would help reduce the capacity and conflict misses. Okay, question? Okay, so we have showing that blocking and tiling can reduce the conflict misses and capacity misses. Now, can we do better? Can we do better? So I'm introducing matrix transpose. Okay, I'm actually adding more instructions now, right? originally it's just matrix multiplication, but right now I have matrix transpose as well. So I'm doing more work, right? Typically, you would think that's a no-no, right? So with matrix transpose, I'm doing transposition here, and then because it's a transpose matrix, instead of multiply a row by a column, right now I can multiply column by column. Sorry, row by row, right? So let's see how effective is that. Where's the, okay, so here's the code of the transposition, the transposed version, right? So as you can see, instead of IIKKKKJJ, it's now IIKKJJKK, right? So let's run it and see how effective is that. Okay, it will take a while. It will take a while. And in the meantime, I also run together with a few different options. Okay, here we go. We got some output now. So the upper half is the transposed one, and the bottom half is the original block version. So let's focus on the 2K. So for 2K with tile size 8, with transposition, how much time we take? 3 seconds, only 3 seconds. And previously it was 4 seconds, right? So even though it sounds like transposition is doing more work, but it further brings down the execution time, right? And another interesting thing, right? Like let me summarize some interesting point in this table, is that for the transposition, right? If you look at why we bring down the execution time, it's because originally we set like 16, it has fewer loop control, but has higher miss rate. With transposition, we actually fix that miss rate problem. So what kind of miss are we removing here? All right, let's take a look. Okay, definitely a case that we want discussion. So why don't you go ahead and discuss with your friend for another 90 seconds and let's see what's going on. All right, after discussion, more of you think it's D. Tell me about why. Why do you think it's D? More sounds safer. Okay, so in a toggling algorithm, how do we, so the only thing that some of you don't agree is capacity miss, right? So in toggling algorithm, how toggling algorithm address the capacity miss?
It divides it into blocks so that the cache can fit.
Okay, divide it into blocks so the cache can fit. Do we do anything different regarding the tile size here? Not at all. So are we changing the capacity miss behavior here? Not at all. So clearly, we only address the conflict miss problem, right? So if you look at the original version of the tile blocking, right? As I mentioned, if I work on the later part, then I'm going to kick out the stuff from the upper tile, right? But is it indeed the case that I never use the upper tile? The answer is no, right? Because now we may come back again for the upper tile, for example, to compute another part of, like, for example, this part of the columns, right? So this upper tile, we still need them, right? How matrix position can help? So for matrix position, right? Because everything is horizontal now, right? If I want to work on the bottom part of this matrix, originally the bottom part of this matrix, it would actually be now here instead of here if you transpose the matrix, right? So what happened is when you work on this part and this part, they are around. They are still around. They are not kicked out, right? So what does that mean is that the conflict misses because this part kick out this part is gone, right? And because you can continue working on the second part without worrying about keeping this tile around, right? Originally, we chose to go down because we want to keep this as longer as possible. But right now, if this is not an issue, we can keep going down and we can keep going there, right? So we are actually eliminating a lot of conflict misses. And if we keep going this direction, there is no such an issue that the lower part would kick out the upper part, right? So basically, you can keep going this direction with a larger granularity without worrying about the conflict miss problem, right? So that's why we can make the tile size larger, but still the miss rate is lower, even though we produce a lot of cache misses to transpose and cache accesses to transpose the matrix. Worth it. Still worth it, right? So actually, we remove conflict misses, but we have nothing to do with capacity misses because the total amount, the working set size, is still the same when we are performing each tile matrix multiplication. Okay, so matrix transpose basically change the data layout, helps to alleviate conflict misses. And so far, we talk a lot of things: conflict misses, capacity miss, conflict misses, capacity miss, conflict misses. What's the remaining type of misses that we haven't addressed? Compulsory. Can we do anything? So here we go. To address compulsory misses, there is a mechanism called prefetching. So if you think how prefetching the idea will work, right, you can go ahead and take a look of your program. As we said, if your program has good locality, the behavior of your code should be really predictable, right? So for example, if I'm linearly traversing an array, right, you are likely to just keep going through the index and increment the index, right? And for this pieces of code, we can imagine when I access D0, there is going to be a compulsory miss. And when I am serving this compulsory miss, my code cannot make progress. I have to wait for D0 to come back, right? So I'm doing access from the L2 to get D0 to D7 because I have to be block in, block out, right? So now when it returns, I can continue to work on D1. But for this D1, because it's already within a block, so it's going to be a hit, right? And then until I meet D8, I'm going to see another miss and access L2. That's the current progress. That's what we have currently in the architecture, right? But think about this, right? If your code is really predictable, I know after this block, this is what you want. I know after this block, this is what you want, right? So here's the thing, with prefetch, okay, I see you want D0, but in the meantime, let's also get the next block together, right? We only have one cache. Cache can only serve one element each time. So we still prioritize serving the block containing B0, right? However, when we finish serving B0, the channel between L1 and L2 is actually free because you are doing the rest of the work for D1 and D8, right? So in the meantime, if we allow the access of D8 to D15 in L2 first, when I really need D8, it's already in my L1. So the following access will all be hit. You are not seeing any compulsory misses anymore. That's called prefetch. That's called prefetch. So there are many different ways of doing prefetch. So, but the golden rule is that you have to make your code easy to predict to make the prefetching working. So in fact, most of the time when you are doing your assignment, your lab, sometimes you don't see the miss rate reported is as what we calculated. So this time I didn't ask you to use those numbers directly because Intel processors, they have pretty good prefetcher. And if you look at the sample code that we gave you, they are pretty regular. So, yes?
Because I remember that one of the questions that calculated like the miss rate to be 0.125, but then it was showing like something like 0.02 something. Is it because of the prefetch?
That is true. So the thing is that sometimes in that case, it's not because of the performance counter is wrong. It's not because your calculation is wrong. And in the assignment, right, there is a like a triangle you can click. In the details, I do give you the explanation. When you click it, you will figure out I did say prefetch there, right? And for some of the questions that you guys are struggling, take a look of the details that I said. It will give you hints. But okay, set it aside. There are two ways of doing prefetch. So first of all, your processor can do prefetch. And sometimes, if you think your code is not that easy to guess what's going on, you can manually add prefetch instructions. So for example, there is an prefetch intrinsic in x86 compilers in C programming language. You can specifically ask the processor to prefetch at a certain point of time. And GCC also have a flag that can automatically analyze your code and see where we can insert those prefetch instructions. And right now, I'm going to show you what we can do with prefetch. So here is the matrix transpose code with really low level. You probably don't want to read this, but there is indeed a prefetch here. So we do a lot of pointer stuff here. So this is a very optimized version. So let's see how much time it takes. And here I'm choosing a 2K by 2K matrices. So this is a machine that I have for most of the demos, right? So as you can see, without prefetching, it's about 0.12 seconds. With prefetch, it does goes faster with 0.001, right? But sometimes it depends on what machine that you are using. You may have different performance again. So for example, this is a machine that with an AMD processor. So for AMD processor, you can see it's also it's now 0.115 to 0.107, right? And this is another AMD machine that I have. So for this machine, right now it's 0.1 to 0.9, right? And there's another machine which is an older machine. So for this machine, it's more significant benefit because its prefetcher is more outdated than the current modern one. So you can see prefetch is also a technique. It works really well if your hardware prefetcher is not that effective. But if you have really regular code, most of the time the hardware prefetcher can do a lot of stuff. So that's why more advanced version of the Intel processor, like the very first machine that I show you, it's really insignificant performance difference. However, for this machine, which I have purchased like 5 years ago, right? This one, its performance gain is more significant, right? So here's a summary of all the software mechanisms that we learned. So prefetching is the mechanism that we could alleviate the compulsory misses if you do it right. So those will give you a pretty good summary of what we have learned so far, and this would cover everything that you need to know for the midterm. And I know you are here for a reason, so let's talk about in the midterm. I start to see some of your face start to change. So here's the format of the midterm. So we are going to have 15 multiple choice questions, and each of them worth 2 credits and a total of 30%. And a majority of them, of your scores, are coming from the assignment style free answer questions. And it's a closed note, closed book, no outside materials available, allowed exam. And multiple choice questions, so I'm giving you some sample questions. You should be able to find all their answers from the slide. So it's a pretty good practice that you can try after you are done with your study. And don't forget to review your reading quizzes, although they are simple, but they might be useful when you are preparing your materials. And there are a few things that I want you to remind yourself and better to memorize them because they are really important and you will use them for free answer questions because every time I really want to ask you to write those equations down, right? So for example, there aren't that many equations that you need to memorize. So for example, the classic CPU performance equation, what's the meaning of each term? What's MDOS law and what's the meaning of each term? And what's C equal to ABS? What's the meaning of each term? How to use it in real architecture. So those would definitely be problems in your midterm. And we spend a lot of time talking about performance equations. So definitely, and that's actually the most basic equation you should know. So there's definitely going to be a problem there. And this is actually one of the pop-up quiz during the class. So don't ask me for a solution, you have it. And this question, again, you have the answer. And for this question, you should have the answer on Sunday after I announce the solution because this is from your homework. And this is also from your homework, but with different set of arguments. And practicing MDOS law, again, this is a question from your slide. This is also a question from your slide. So this is a sample midterm. And the style of questions is pretty close to what I show you here. So definitely go ahead and practice all of them. They are not going to be 100% the same, but the style is pretty similar. So announcement, we have an update to assignment 2, so don't forget to poll the latest update. And midterm, I think I have good enough explanation there. I have an office hour starting from right after the class to 6 p.m. So if you have any question, come to my office and I will try to help you out. And reading quiz 5 due next Wednesday. So if you think, okay, midterm is just a piece of cake and you want to work on something else, I still prepare something for you. Other than that, enjoy the rest of the day. I will see you next Tuesday.